Have you ever looked at a complex piece of machinery and just wondered, how do they know? How can an engineer predict down to the tiniest detail exactly how much energy a chemical reaction is going to produce? Well, it's not magic, and it's definitely not guesswork. It's a precise science. So let's open up the toolkit engineers use to calculate the very energy that powers our world.
So, let's start with something familiar, like this furnace. The idea is simple, right? You burn some fuel, you get some heat. But for an engineer, the real question is, how much heat? I mean, exactly how much? Because if your math is off, you might just have an inefficient system that costs a ton of money to run. Or you could have something much worse, a system that's downright dangerous because it can't handle the energy it's unleashing. Precision isn't just a goal here, it is everything.
To get that kind of precision, engineers turn to a law of the universe that you've probably heard of, but maybe never thought of this way. It's called the energy balance.
Now, the beautiful thing about this is just how simple the core idea is. Seriously, think of it like your bank account. You can't just invent money in your account, right? Your final balance is always just what you started with, plus all your deposits, minus all your withdrawals. That's it. Well, energy works the exact same way. It all has to add up. It's just accounting.
And this equation right here, this is basically the engineer's checkbook. Don't let the symbols intimidate you. It's just a way to track everything for what we call an open system, where stuff is constantly flowing in and out, just like in our furnace. The Q is tracking heat, the W is for any work being done, but that delta H term, that's the really crucial part. That's the energy of the actual materials flowing in and out of the system.
But here's where it gets tricky. What happens when there's a huge, unexpected deposit or withdrawal of energy happening right in the middle of your process? Well, that's exactly what a chemical reaction is. It is a massive energy event that has to be accounted for perfectly.
So, to deal with that complexity, engineers have two main ways to tackle the problem. Think of them as two different specialized tools in the toolkit, each one perfect for a specific job. Let's take a look at what they are.
Okay, so on one side, you've got the heat of reaction method. This one's direct, it's efficient, and it's your best friend when you're dealing with a single, well-known reaction. It basically just measures the total energy change from start to finish. On the other side, you have the heat of formation method. This one is way more fundamental. It breaks every single compound down into its basic building blocks. We're talking pure carbon, hydrogen, oxygen, and it builds the entire energy picture from the ground up. This is the one you grab when you've got a really complex system with lots of things happening at once.
And you know what's really cool? No matter which of those two tools you pick up, the general game plan is always the same. First, you draw a map of everything going in and coming out. Second, you balance all the materials, because you can't create or destroy matter either. Third, you pick a starting point, a zero for all your energy measurements. And finally, step 4, you get organized, put everything into a table, and solve the puzzle.
All right, theory's one thing, but let's actually see how this works. We're going to go back to our propane furnace and figure out exactly how much heat that thing is kicking out.
Now, since we have one single, clearly defined reaction, propane burning, the choice is obvious. The heat of reaction method is the perfect tool for this job. We know what's going in, we know what's coming out, so let's calculate the energy.
And this right here is a perfect example of that meticulous organization I was just talking about. This is step 4 in action. You build a table just like this one to track every single substance, the propane, the oxygen, the nitrogen from the air, you name it. You quantify its flow rate, its energy state, everything. This is how you set yourself up for that final calculation.
So after all that careful setup, you run the numbers through the energy balance equation, and this is what you get. It's a huge number, but what does it actually mean?
The single most important detail on this whole screen is that tiny little minus sign. In the language of thermodynamics, a negative number for heat means energy is leaving the system. It's what we call an exothermic reaction. Our furnace isn't soaking up energy, it's releasing it. And it's releasing a ton of it. Over 126,000 kilojoules every single second. That is a whole lot of heat. And now we know exactly how much.
So we figured out the energy for one furnace. Big deal, right? Well, actually, it's a huge deal. Because the logic, the math, the very process we just walked through, it applies to an incredible, almost unbelievable range of things.
Seriously, just think about it. From designing the power plants that keep our lights on, to developing the life-saving medicines in your cabinet. From creating the next generation of batteries for our phones and cars, to making sure a chemical plant is built safely. It all comes back to mastering this one skill, the energy balance. It is truly one of the absolute cornerstones of modern science and engineering.
And that really brings us to a final, pretty big thought. As we look at the challenges ahead of us, finding new, sustainable energy sources, building more efficient technologies, and getting a real handle on climate change. This ability to perfectly track and control energy isn't just some abstract engineering problem anymore. It's the key to designing our future. How we choose to balance these equations today will literally determine what's possible for all of us tomorrow.